Yesterday, we learned how to do vector addition and subtraction, and we also learned what a vector is. So, a vector it has direction and it has a size to it. And as the week goes on, we'll learn different properties and things that we can do with vectors. Today, we're going to focus on scalar multiplication, and then I'll show you how to multiply two vectors. Vector can be 2D if it just has an X and a Y, or it could be three-dimensional if it has an X, a Y, and a Z. So we'll take a look at a vector that's just two-dimensional, and then we'll take a look at some that are three-dimensional. So a scalar, as we talked about a couple of weeks ago with matrices, a scalar is a number that you multiply by. So a scalar only has magnitude. It only has size, 5, 1/2, 11. So it only has size. A vector has a size and a direction. So vectors have magnitude and direction. So that's the difference between a scalar and a vector. So if I see something like this, K is normally what they use to represent a scalar by, but we know that the variable can be any variable that we want to. And then B is whatever the matrix, whatever the vector is. So a scalar, we will multiply that times the vector. So these are very straightforward, very, very similar to polynomials. The only difference is now we're working with vectors. Number 1 says multiply the vector b 2, 9 by the scalar 7. So all that means is to take 7 and multiply by 2, 9. And we do the distributive property just like we've been doing for a while. 7 times 2 is 14. 7 times 9 is 63. And just like that, we have multiplied a scalar. In this case, it was 7 by a vector 2, 9. Number 2. I'm going to do the exact same thing. Again, just as far as the notation goes, you may see it written out just with these little V brackets here, or you may see it written out with the variables. So this particular vector is a three-dimensional vector. I have J, and I have K. So this is X, Y, and Z. So if I were to graph this, I would have to graph it 3D in a 3D plane. But we'll go through. We did the distributive property. If you need to put your arrows up there at the top, there's nothing wrong with that. So negative 2 times 3i is going to give us negative 6i. Negative 2 times negative 4j, we're going to be careful with our signs there. And negative 2 times 9 is negative 18. And I did want to throw a fraction at you because there's nothing wrong with a fraction. I take that 1/2 and I multiply everything by 1/2. It's okay to get fractions. So we get 9/2 and we get negative 2. So that is scalar multiplication with a vector. Whatever's on the outside, take that and multiply by whatever's on the inside. Now I do want to take a look at multiplying two vectors. There we go. So when we're multiplying a vector times a vector, if it's a two-dimensional vector, I take this first number, multiply by this first number, and add it to the second number times the second number. If it's a three-dimensional vector, I take the first vector, multiply it by the first number here. I take the second, multiply by the second, and then I take the third and multiply by the third. Now, I know that this may look kind of crazy, and I know that it may look kind of difficult, but we've actually already done this semester when we were working with matrices. This is called a dot product. So we did this when we multiplied matrices. We did the first times the first and added it to the second times the second. And in this case, there's 3 of them. So we did the third times the third. So for example, number 1, this is a 2D vector. So we're going to do 5 times 2 and then add that to 7 times negative 3. So that is a dot product. Again, 5 times 2 and add it to 7 times negative 3. You're only going to get a number back, and that's okay because we're trying to figure out what is the magnitude, what is the size when I multiply these two together. So there is nothing wrong with that. So if I set up my steps there, we're doing 5 times 2, and we're going to add that to 7 times negative 3. 5 times 2 is 10. This gives me negative 21. I add that together, we get negative 11. So you're only going to get a number back, and there's nothing wrong with just getting a number back. Number 2, same thing. We're going to do the first times the first and add it to the second times the second. So 2 times 8, and I'll write that step out in case you need it. So it's 2 times 8 plus negative 1 times 3. So 2 times 8, negative 1 times 3, add that together, gives us 13. So first times first, add it to second times second. Let's take a look at this 3D vector that I have down below. So I'm going to do negative 3 times 1, add that to 5 times negative 7, add that to 4 times 8. So first times first, add it to second times second, add it to third times third. So that's going to look like negative 3 times 1 plus 5 times negative 7 plus 4 times 8. So negative 3 times 1, the second times the second, and the third times the third. Then we'll go through and multiply. This gives us negative 3. This gives us negative 35. This gives us 32. Okay. We add these together. This is going to give us negative 38. This is going to give us 32. And it's going to give us negative 6. Oh, sorry there. Negative 6. So first times first, add it to second times second, and if it's a 3-dimensional vector, then we do third times third. Before we end, I just want to go through and take a look at some properties that are true for a dot product and vectors. So this would be dot product and vectors. Vectors. So if I do A times B, that's going to give me B times A. That's going to be the exact same thing. So we call that the commutative property. So 5 times 3 is the same as 3 times 5. So when you're multiplying vectors, they are commutative. So the first vector times the second vector will give me the second vector times the first vector. So the vectors are commutative. Vectors, we've already seen that we can go through and do distributive property with vectors as well. So that holds. So the distributive property holds with vectors. And we also should know that anything times 0 gives us 0. So this is the 0 property of multiplication. So most of these, if not all 3 of them, hopefully were intuitive for you, meaning it just kind of makes sense from the knowledge that you already know. But just in case, these 3 properties do hold for vectors.